Now let's talk about real work and about characteristic of forces to be either conservative or not conservative. This is probably a concept which you already studied in physics classes, but we will look into it because it basically uses the same equations we have been using so far, so it's a good way to combine the topics. We are now talking about real work, actual work, not virtual work anymore. So we said conservative force when the work done by a force depends only on the initial and final position of the force, and it's independent from the path that it travels, then the force is referred as a conservative force. So an example of conservative force is gravity, so weight. Let's look at this block moving on a surface from position A to position B. Now we are looking into a motion without friction because we are only looking at the effect of weight, so we don't want to contaminate it with friction. The work done, as per definition that we have discussed through this chapter, is du is equal to the weight W, which is a vector, scalar product dr, which is the displacement. So this is a scalar product, so it becomes dot product. So it's a scalar, and it becomes W dr cosine of theta, where theta is the angle between the weight and dr. Now dr cosine of theta is clearly, if we look at the triangle, this triangle here, dr cosine of theta is equal to dy. So this is equal to W dy. Okay, so the total work, because this is the differential work, is going to be, let me move a few things around, so we keep this here, we can keep the triangle for now. Total work is going to be the integral of all the differential work. It's going to be negative because the weight is in the opposite, in this case is in the opposite direction of the displacement. I'm lifting the box, so the displacement is going up, the weight is going down, so the scalar product will have a negative sign. Integral between I call the initial point 0 and the final point h, weight dy, and this is just minus w times h. So the work only depends on the vertical displacement, and that's through whatever trajectory I use. So I can lift my box directly from here to here, or I can follow this path, or I can follow whatever path I want. At the end, I can go up and down how many times I want. If there is no friction, the work is going to be only due to the different height that the box had from initial and final point. So weight is a conservative force. Let's look at another conservative force. which is the force of a spring. So in this case, this is the schematic. The work done by the spring is again du equal Fs, force of the springs, times ds. And the force of the spring is depending on where is the undeformed position. In the picture I'm looking at, considering that I'm moving right to the undeformed position, the force is going to push left, so the force is going to be opposed to the displacement itself. Sorry, the displacement is also a vector, so there is a minus, and it's going to be the spring constant, the displacement s, the position s times ds. The total work is going to be again the integral between whatever initial position and whatever final position of this differential work du, so minus k s ds. And so if I integrate s in ds, I obtain the square. So it's minus 1/2 k s square of the final position minus k s square of the initial position. So again, the work done by the spring, it's only depends on the initial and final position. Doesn't matter what path it's gonna take. It doesn't matter how many oscillation it's gonna do. You can go back and forth as many times as you want. At the end, the work done is just going to be the difference between the initial position and the final position, but squared. So let's look at the force that is not conservative force, and that's friction. Friction depends on the path you take, because it's if you remember, when I have a block, and this block is moving, the friction force is going to be parallel to the displacement. So if this is my displacement s and this is my friction force f, my work is going to be f ds, and in this case the scalar product is going to be actually equal to f ds. So when I go to integrate and to obtain the actual work between two positions, since my my force is gonna depend on the length of the section that is gone through, is not just gonna be the final and initial position, but it's gonna be the path. Just think of sliding a box on the ground. You're gonna do more work if you take a longer path rather than taking a shorter path. And it's not like a box going up and down, where in the moment it goes down, the box is doing work towards you. In the case of sliding a box, you are always gonna do the work, no matter what path you take. So it is not a conservative force. An interesting application of conservative force is that we can determine potential energy. So Since the work done by a conservative force only depends on initial and final position, we can define a property called the potential energy, which depends on the position with respect to a certain reference. So we need to define what this certain reference is. It's the book calls it a datum, which is a reference position. The datum is the arbitrary point with respect to which we will measure the potential energy. Basically the potential energy is the work done to bring, in the case we are lifting the box, to bring the box up there, so it's going to be this Vg is equal to the weight times the height, and if we're bringing it down, it's negative with respect to the datum. There is also an elastic potential.